specialty of the tree data structure, we want some kind of a data structure where there is a link with parent and a child. So basically one, this is a parent. The parent has a child node, the left child and the right child, technically calling this. Okay. And now this is having the left child as 4, 5, 6, 7. Okay. This kind of a data structure, we were talking about the link, right? In the linked list where it is pointing to the left, doubly linked list point to the previous and to the next element, right? So now if I would say the previous value and the right. So this is a doubly linked data structure. So where there is a value and there is a reference to the previous node, and then there is a reference to the right node, or let me call that as a next node more technically. Similarly, here we will have a previous value and next. And if we wanted to do a link between this, right? So whatever the address this node will have, this next needs to point to this node, right? And then this previous one needs to point to this particular node. I do not want to get into too much detail of the doubly linked list at this point of time. But now we are talking about the linked base, right? So basically this is one node. This is an another node. So we can define our data structure, right? Considering that we wanted, there would be two goals, right? The one goal would be store the value for whatever data structure we create. First goal is to store the value. And how do we want to refer to the other node? So in this case, in case of doubly linked list or linked list, one node is always referring to one node. It is not referring to more than one node, because this node is referring to the previous in this case, next in this case, right? And in case of linked list, it is always referring to the one node, next node. The linked list does not have the previous, right? This is a doubly linked list. So here we wanted to refer in a sequential order. Okay. But in case of tree data structure, where we are storing the value of 1, and here we are keeping the links in a non-linear fashion. Here it is referring a link to the child node, and we are calling as a left child and a right child. Similarly, left child and a right child. Okay. Always we have a access to only one node at a time, as we have seen in our last session. With that one node, how do we traverse to access to other node? That defines what kind of a data structure we need. I repeat once again, this is important. We always have only one access to a node in these data structures. How we traverse, how we read to a different nodes, that defines what kind of a data structure we need to create. For example, if you wanted to just move forward, we use a stack, queue, linked list. But if you wanted to move back as well in a linear sequential order, we use a doubly linked list. But when actually we wanted to have some data structure, which is in a form of a tree, and we can move left or right, for some of these scenarios, what we have seen, if the tree is balanced, we can avoid the complete traversal of the left part. And with that, we will be able to traverse with log of n time complexity. Then we use a tree data structure. Okay, so let's do some hands-on. Lot of theory we have talked about. So let's create this data structure. Okay, so you will not see in Java there is any data structure, something called tree, similar to the doubly linked list. So in Java, you would see that there is a data structure called linked list. There is a data structure called stack, queue, right? But you will not see that there is any collection called doubly linked list. You won't see any collection of type, any class of type tree here. We have a tree map, but that's a different. But you will not see a tree data structure in Java. Okay, so it means that now you basically need to understand this concept, and you need to customize. You need to customize your data structure to form a link. Okay, so with that, now the part of this exercise is basically we have a reference to the node of this tree data structure. Okay, so let's say we have a function called traverse, and in this traverse function with the type of tree, right, we are getting the head node. With this head node, we wanted to print, access all the node and print all the numbers in the uh, in the order, right? In the order of the breadth first. Now, what is breadth first and depth first? And what is the difference? What is the implication of each? Another is in a simple term, if you just touched upon in a simple term right now, the breadth first is basically it's an spiral way when we are traversing. That is our learning strategy as well. So it means we are first touching upon all the things together, and then we are incrementing it, and then we are touching upon all the thing and then incrementing it. This is called a breadth first approach. In the depth first approach, if we wanted to do, what we do is we go in really one area in deep, right? And then we come back, then we go here and then come back, go here, come back, right? This is the depth first approach. Depth first means we are going depth first. That is why it is called as a depth first approach. The practical use case for this is, right, and when do you need what? The practical use case is, think about that you in the city, right? You are in your home. Okay, this is your home. Now here, this is the entire city. Okay, now you wanted to find some person who is somewhere in the city, right? You don't know where is that person. The person could be in hospital, could be police station, could be railway station, airport. So you wanted to go and search for that person all over the places in the city. Okay, and you may find a person anywhere. You may find person here near to your home, or you may find a person very far from your home. Okay, so what would be your approach, right? Your approach could be, maybe you can think about some assumptions that it is very highly likely that person might be on in that police station that is somewhere. So you'll go to that place, and then maybe you'll say, okay, you find that person or not. Then you will assume that the person might be in the airport, right? Then you will go and find that person here, right? But at worst scenario, you will be ending up searching the entire city, all the places, and then maybe you will find some person here nearby. Okay, but at worst case, you will end up searching all the nodes. You can assume it could be nearby, and you can search in these areas, right? But at the end, if you won't find that person, if the person is very smart, or like there's intention of hiding himself somewhere, then you will end up searching all the nodes in this tree, in this graph, right? So we'll talk about the graph with more after few more sessions here. For now, think about tree, graph together. Anyways, those are linked. So the graph nodes, how they are linked to each other, that makes the difference between trees and graphs. Okay, but for now, let's assume tree, graph in the same category, and we end up traversing all the nodes here, and that's why the time complexity here would be O of n. Okay, similarly, if you say that no, I do not wanted to assume anything, I wanted to first search nearby, because it's highly likely that person would have not visited distance more than 2 kilometer by that time, right? Then you will start searching about the nearby location first. If you find that person not, then probably you will increase your distance here. But it might happen when you are searching in this direction, the person is here, the person is keep moving here, right? So you will, when you are traversing, right, when you are going in one direction, you will think about like, this could be the best approach for my use case as compared to DFS. Then maybe I want a BFS. But always there will be kind of a drawback for the worst scenarios, right? Like if you're traversing here, let's say the person is here, but again, if you're traversing here, by the time you reach here, the person would have moved here, and then the cycle continue, and then you will find the person at the boundary, right, at the edge of the city, because person cannot move out of the city, let's assume. So you will end up traversing the all the nodes of this graph with O of n time complexity. Okay, so now when you're going from your home to your office, right, and a map, right, if you're using a Google map, it is using the algorithm of the shortest path to reach your office, right? So but that is a weighted graph. Weighted graph is the traffic when you wanted to visit from your home to your office, right? What all different direction it could be, right? But these are the like minimum, the shortest path, right? There is an algorithm for that, right? But these are the weighted graph. So now in this use case, also there is a weight here. The weight is the traffic here. Depending upon the weight, we wanted to see which direction we wanted to go, right? So now you can think about, right, just as a DFS approach here. DFS approach here, when you are calculating this, right, the time and all that. So you need to evaluate all these one, two, three, four, five direction. How much time it is taking? Let's assume there are total five direction to reach your office with weights, right? So you will go and check in this direction how much time it is taking based on the traffic. Let's say it is taking a very hypothetical number, right? A 5 minute. Then you go and get into this and check how much time it's taking. 8 minutes, 10 minutes, 15 minutes, 20 minutes, right? And based on that, you give. This is a basically DFS approach. Now you think about, like, maybe I can think about the breadth first approach as well. Covering the 1 kilometer, how much each of these times are taking, like 1 minute, 2 minute, 3 minute, then this much distance, then this much distance, then ultimately covering the 5 kilometer of distance as a cumulative one, how much total time would be for each of these. So in these two scenarios, you would see, right, both are same, right? Most of the time, you will see that one is better than the other. Maybe I'll use this BFS, not the DFS, or in some scenarios you'll see that there is DFS, I will use not the BFS. Okay, but those are basically the, the assumptions what we are making, that this in the best, there is something called a best case scenario and the worst case scenario. This is also I want to talk about as part of this best case scenario and worst case scenario. And this is always a average. Okay, with that we will understand what is the difference between why we talk about best case, worst case, and what is the average here. Okay, so in most of the cases, most when you write an algorithm for most of the questions, coding questions, or when you encountered all this problem, you will see more than 90% of the time there is no difference. Basically, you basically go with the DFS or BFS. Ultimately you will have to traverse all the nodes ultimately. So whichever you write, whichever you're comfortable, go ahead with that. More than 90% of the cases we will see, like, we go. Okay, and that's called something called a average. Average means we will think, we will not assume anything, we will think that anyways we, it could be anywhere, right? So that's where the time complexity is. Some of the scenarios you will be able to justify with the best case scenarios, right? That you will say that I know the person can, maybe he or she will go at the police stations, or only at the famous places which is at these distance. So that's why the best case scenario would be like log of n for DFS approach, but the best case scenario for in the BFS it would be still O of n. You will be able to justify with that, that concept, that understanding you should have, that explanation you should be able to give. Okay, uh, but at the end the best case and worst case scenario doesn't work in practical use case. We know, like, whenever we do something, generally, but we do not assume that those things happen in production. So that's why these things are considered, and you should know all these scenarios. Okay, let's get into the BFS approach now. Now you guys understand what's the BFS approach. BFS approach, to print the numbers in an order. So it means BFS is like when we print the one here, then we go from here again, and then print 2 and 3, and then again we go here and we print 4, 5, 6, 7. At the same time, you need to think about, right, basically this is a code, right, which you wanted to focus on, you wanted to complete it. How these trees are creating, that's not the goal for today. Okay, but you need to define this tree class. How do you want it to have this tree data structure defined? Okay, maybe you guys can do this exercise, but I'll give some pointers to this as a skeleton, so that you would be able to think about it. First, let's define the tree data structure. In this tree data structure, we know that we have a value and we have a link to the two different nodes. Similarly, this node also will have the same thing, right? And these node we are calling as a basically a child node, left child and the right child. But if you see, this parent and child node have the same structure. Structure wise, it's not different. All nodes are same, right? It's just the access, we have the access to this head of this or the parent root. More technically, this is called as a root node of the tree. Okay, with that, let me update here as well. Let's call this as root node. So this is pointing to the similar data structure. because there is no difference between these two, right? So it means something like it is pointing to itself or it is pointing to something else, but both belongs to the same type with left and right, and it is having a value of an integer format. So that's why our class would looks like a tree, right? And let me call this is more specifically not as a tree, right? The tree is the concept here, because tree, this whole thing is a tree here, right? But what does the tree contain? The tree contain the node. This is a parent node, this is a left node, this is a right node, and the bottom ones who does not have the childrens are called the leaf node. Okay, so with that, let me define here a class as node, right? This node class, what does this node class contains? This node class contain first is primitive type value. This is the value of the node. Then it contains the reference, the link to the left child and the right child. Whether it's a linked list, doubly linked list, whatever it is, always consider the same structure here for creating the references, because it is of having the same type as we see here, right? So this is of the same type, and let's call that as left. Similarly, the node, let's call that as right child, as right. Okay. So you have created this structure now. And now if we are passing this structure to this function node, so you have reference to this node in this tree, right? You wanted to print 1, then you need to print 2, 3. But as soon as you go here, right, at 3, how you will be able to access the node 4 here, right? Similarly, as soon as you are printing from 2 to 5 here, right, how you will be able to access 3 here. So we need to think about in this kind of a when we are trying to solve this kind of a problem, right? So there is something that we always have a reference to some node where we are manipulating its value by printing or editing it. At the same time, we should have some way to get back to a different node based on our requirement. For example, if we are printing a node of 4, we should have a some way that we should be able to access to 3. Depending on it, we wanted to choose that data structure. Okay, so now you see, right, when you are printing it 2, right, and then you are printing it 3, 4, 5. So you would see this is in basically in an order here, right? This is an order, and whenever we print this, right, we always go back to the previous node. So when we are printing it 1, right, and then we have a access to 2 and 3 only at this point of time, and we know we the next one we wanted to print as a 2, right? When we wanted to print a 2, we only have access to 4 and 5, but we know that the next element we wanted to print at 3. So you see, this is looks to be something kind of a uh, FIFO, first in and first out order here. So when we access to this, we wanted to print this access to 2 and 3, insert 2 and 3 into some data structure. We don't know at this point of time which data structure it is, but we are inserting 2 and 3. So let's print 1 here, right? We have access to 1, right? Now from when we access to 1, we have access to 2 and 3. So let's put 2 and 3 in some data structure. We don't know which is that. Okay, but we are adding 2 and 3 because we have access to 2 and 3 right now. Now let's remove this 1 from here and print it. Similarly, when we get into 2, right? So when we get into 2, what we do is we remove 2 from here, print it, and the left and right of these 2, we add into the same data structure. So 4 and 5, it's added, done. 2 is removed, printed, added 4 and 5. Next is we will see which is the next node where we have added into the data structure, which is 3. So let's remove 3, print it 3, add the left and right of these 3 into the data structure, 6 and 7. Similarly, let's remove 4, print it. Does it have children? No. So let's not add into the data structure. We need to have those check if it having those children. Similarly for 5, 6 and 7, print, print, print. We will be able to print into this sequential order. This is called printing it into a at first approach.